So again, we'll finish off the topic by thinking about sample size. Two sample sizes. Right? How many first unit? How many first phase units should I take? And how many second phase units should I take? N1 and N2. For completeness, the formulas are on your formula sheet, but they don't fit on a slide. That's not true. I like to think of them, report them, talk about them graphically. And so that's what we'll do. And these graphs are in a handout for today. If you were given an exam question about sample size under double sampling with a regression or ratio estimator, I would give you these graphs. The graphs are just the equations in pictures. We will only look at, for illustrative purposes, the regression estimator. Same thing would follow for the ratio means estimator, but we'll just look at the regression. I want to define some symbols. N subscripted by SRS. We will use as a basis the sample size you would need to take if you use simple random sampling. So if you had no auxiliary information, or you weren't smart enough to make use of it, NSRS would be the sample size you would need to take to achieve the precision you need to achieve. Everybody with me? That's the base. C1 and C2. C stands for cost. C1 is the cost of a first phase unit. C2 is the cost of a second phase unit. What's the relationship between C1 and C2? If we would ever consider this technique, what's the relationship between C1 and C2?
C1 is much less than C2.
Yes. C1 better be much less than C2. Otherwise, I'm wasting money. Because I don't care about the X's. I'm just using them. I care about Y's. But they're much more expensive to observe, we're assuming. And then finally, R, correlation coefficient. Or its population equivalent, Greek letter rho. So correlation is an estimate of what's going to appear here as rho. True population correlation. Correlation between X and Y, right? Correlation between the auxiliary variable and the variable of interest. So first graph. This is first phase sample size as a ratio of NSRS for different values of correlation. And here I'm assuming the correlation between X and Y is positive. Doesn't have to be, but I'm assuming it is. The interesting thing about this chart, the smallest value for that ratio is 1. What? You're telling me I'm going to take more first phase units than I would have to take in simple random sampling? Yeah, sometimes up to 2 times more. That's got to be wrong. No, it's not. Why? Why will I be taking more? Or why is it not ineffective to take more? What's the difference?
you have your variable of interest and your auxiliary variables.
Yeah, exactly. My first phase sample size, each unit's gonna cost me a lot less. So I can afford to take more of them. Versus a simple random sampling, I'm observing this thing that costs me a lot. So the first phase sample size is almost always gonna be bigger than what you would have to take under simple random sampling. It's gonna cost you a lot less usually. I have 3 different lines here, 3 different curves, and they are all based on the cost ratio. So this is a cost ratio of 2. Cost me twice as much to observe Y as X. This is a cost ratio of 4, 4 times as much to observe Y versus X, and then 8 times. For that timber cruising example, I mean, it depends on how you measure, right? But that cost ratio is usually 6 or greater. Costs you that much more, usually more than that, to observe volume versus swinging a prism and getting base load. So you can see that, generally speaking, as the correlation increases up to a point, I'm going to take more first phase units. What if the correlation was 1? Will it ever be 1? First I should qualify. Will the correlation between the auxiliary and the variable of interest ever be 1? No, it'll never be 1. But let's just think about it. What if the correlation was 1? On how many units would I observe Y? 1. Or maybe 2 if I needed a regression estimator, right? If it's a perfect correlation, X is telling me everything I need to know about Y, except what the actual relationship is, right? So I need 1 or 2 of those units. Right? Because X is much cheaper to observe. Next graph here, this is the more interesting one maybe. This is the ratio of second phase to first phase sample size as a function of correlation, and then these different cost ratios. And basically it's just a inverse relationship with correlation, right? The higher the correlation, the fewer. The higher the correlation, the fewer units I'll observe Y on. Right? Of course. Okay. So let's say, for example, I have, we'll just pick a cost ratio of 4, and my simple random sample size is 10, just to pick out a random number to use. Simple random sample size is 10. My cost ratio is 4, and my correlation is 0.9. And by the way, what do you suppose the correlation between volume per acre and basal area per acre is if we're measuring the same trees? Anybody want to guess what it is? I mean, it varies, right? But is it like 0.1 or 0.2 or? Okay, it's a lot higher than that. Like 0.95. So let's say it's 0.9, be a little bit conservative. So what we have, N1 over NSRS, 0.94, looks like roughly, we'll take half a million units. So our first phase sample size would be 15, right? We took 10, simple random sampling, we multiply that times 1.5, everybody follow me off the graph? So 15 first phase units. And then again, cost ratio 4, this one correlation 9, let's say it's 0.2. On 20% of those 15 units, I would also observe Y. Right? That formula, which is on the handout for today, tells us when double sampling with a regression estimator will be better than simple random sampling, when it will be better, when you should use it. That's this curve right here. Cost ratio, correlation, minimum correlation for double sampling to show a gain. So let's say our cost ratio is 4. I go up here and I get about 0.75, 0.8. So if the cost ratio is 4 and you got a correlation of 0.8, let's say, or bigger, you better be using this estimator, or you're wasting money. 0.95, or cost ratio for 0.95, our cost ratio can be as low as 2, and we're still gonna do better with regression estimation. Questions?
So this particular slide was on a handout on Moodle?
All the graphs are on Moodle. And this equation is in the summary for today.
Can we go back one and,
Go over that example.
yeah, play around with how you did it?
Yeah, right, so we're gonna say, I already computed that I would need to take 10 units to satisfy my precision requirement under simple random sampling. Okay, first thing given. Second was I assumed that the cost ratio, cost of observing a Y versus cost of observing an X, was 4. Cost me 4 times as much. And then third thing, that's the second thing. Third thing was I'll assume the correlation between the auxiliary and variable of interest, 0.9. Now I want to know what should N1 and N2 be? N1, well, my correlation is 0.9, my cost ratio is 4, so I just said, well, it's about 1.5, looks like, right, over here, 1.5. So 1.5 times 10, 15. 15 units in the first phase. Then I go to this chart, my correlation is 0.9, here's my cost ratio, I said, well, that's about 0.2. So 20% of those 15 units, I'll also observe Y on. They'll be my N2 units. That's the answer.
Didn't you also say something about 10?
Yeah, that was the very first thing I said. I said, we're assuming here that we've done the calculation and the simple random sample size that we would need to take is 10.
And we found out we need more than 10?
Yeah.
Okay.
How many more in the first phase, and what fraction of that in the second phase?
So that's how many more besides 10?
No. This is the ratio of first phase to the simple random sample.
Okay.
So 1.5 times as many.
Okay.
Other questions? Have a good weekend.
I have a tangent question about the.
We're only up about 12. Yes.